Good day, everybody. How are you all? Today we are going to talk about entropy. So, without further ado, I'll share my computer screen with you. So, entropy, a measure of disorder. The second law of thermodynamics states leads to the definition of a new property called entropy, a quantitative measure of microscopic disorder for a system. Entropy is a measure of energy that is no longer available to perform useful work within the current environment. To obtain the working definition of entropy and thus the second law, let's derive the Clausius inequality. Consider a heat reservoir giving up heat to a reversible heat engine, which in turn gives up heat to a piston cylinder device as shown. Okay, below. Okay. So we are doing an energy balance. Energy in minus energy out is equal to delta change in energy. And similarly, delta QR minus in parenthesis change in reversible work and change in system work is equal to change in uh, energy, okay, of the C, where EC is the energy of the combined system. Let WC be the work done by the combined system. Then the first law becomes del WC, or change in uh, of the combined system, change in work in the combined system, in change in reversible work plus change in work on the system. So delta QR minus delta WC is equal to DEC. Okay. So basically, we substituted delta WC in term for del in parentheses. Remember, in the parentheses, it was delta W reversible plus delta W system, change in work, reversible work plus change in work done on the system. For that, we are going to replace that with delta WC. C is the closed system. If we assume the engine is totally reversible, then delta QR, change in uh, heat content of a reversible system divided by temperature of reversible is equal to delta Q by T, or delta QR is you multiply by TR on both sides. Remember temperature, reversible temperature. So the total net work done by the system, which is delta WC, is equal to delta QR minus DEC. For delta QR, you write TR delta Q by T minus DEC. Okay. So basically WC, if you go back to the previous, you can integrate along the path and you get WC is T reversible and integrate along the path delta Q by T minus integrate along the path DEC. Okay. If the system as well as the heat engine is required to undergo a cycle, then DEC equal to 0 because it's going in a cycle. And the total network then becomes WC is equal to TR and then delta Q by T integration. Remember that circle on top of the integration sign means it's path dependent. If WC is reversible, is positive, we have a cyclic device exchanging energy with a single heat reservoir and producing equivalent amount of work. Thus, the Kelvin-Planck statement of second law is violated. But WC can be zero, no work done, or negative work is done on the combined system and not violate the Kelvin-Planck statement of the second law. Therefore, since reversible temperature is greater than zero absolute temperature, we conclude that WC is T reversible, then integration of delta Q by T dependent on the path is less equal to zero. Okay, less equal to zero. Okay, it can be negative work done on the system or it can be zero, no work done. Okay. So basically Q is the net heat added to the system. So delta Q net by T less equal to zero. This equation is called, again, it's path dependent. That's what the circle or oval on top of the integration means. This equation is called the Clausius inequality. The equality holds for reversible process and the inequality holds for irreversible process. The equality means delta Q by net T integration path dependent is equal to 0. It's for reversible process. Inequality is less than 0 for irreversible process. Example 7.1. For a particular power plant, the heat added and rejected both occur at constant temperature and no other processes experience any heat transfer. The heat is added in the amount of 3150 kilojoule at 440 degrees Celsius and is rejected in the amount of 1950 kilojoule at 20 degrees Celsius. Is the Clausius inequality satisfied, and is the cycle reversible or irreversible? So basically, we do a heat balance. So delta Q net by T plus the integration of delta Q net by T less equal to 0, or Q net by T plus Q net by T. So one is in, another is out, is less equal to 0. So Q in plus T divided by T in plus Q net is minus Q out by T less equal to 0. So we plug in the values of Q in and Q out. Notice Q out is negative. And we do the calculation, it is minus 2.237 kilojoule per Kelvin, which is less than 0. Calculate the net work cycle efficiency and the Carnot efficiency based on TH and TL for this cycle. So W net is equal to Q in minus Q out, that is 1200 kilojoule. 3150 minus 1950 is 1200 kilojoule. So eta thermal or efficiency of the thermal is cycle efficiency is W net by Q in is 0.381 or 38.1. And what is the Carnot efficiency is 1 minus TL over TH. Remember, all these temperatures are in absolute temperature. Hence, the Celsius is converted to Kelvin by adding 273. So the Carnot efficiency is, of course, higher than the thermal efficiency. For a particular power plant, the heat added and rejected both occur at constant temperature. No other processes experience any heat transfer. The heat is added in the amount of 3150 kilojoule at 440 degrees Celsius and is rejected in the amount of 1294.46 kilojoule at 20 degrees Celsius. Is the Clausius inequality satisfied, and is the cycle reversible or irreversible? So again, integration depending on the path, delta Q by net by T less equal to 0. So delta Q by net T can be split up into two parts. One is the in and another is the out. Remember, in is positive Q in by T in, out is negative minus Q out by Q out. And we do the calculation, it's equal to 0. So nothing is violated. Left hand side is equal to the right hand side equal to 0. So calculate the net work and cycle efficiency for this cycle. Net work is W net is Q in minus Q out. Okay. And eta thermal is W net by Q in is 58.9. So what is the definition of entropy? Let's take another look at the quantity of path-dependent integration of delta Q by net by T less equal to 0. If no irreversibilities occur within the system as well as the reversible cycle device, then the cycle undergone by the combined system will be internally reversible. As such, it can be reversed. In the reverse cycle case, all the quantities will have the same magnitude but the opposite sign. Therefore, the work WO, which could not be positive quantity in a regular case, cannot be a negative quantity in the reverse case. Okay. Then it follows that W cycle internal review is internal WC internal closed circle internal reversible process is 0, since it cannot be positive or negative quantity, and therefore delta Q net by T path dependent internal reversible engine is equal to 0 for internally reversible cycles. Thus, we conclude that the equality in Clausius inequality holds for totally or just internally reversible cycles and the inequality for irreversible ones. To develop a relation for the definition of the entropy, let us examine this last equation more closely. Here we have a quantity whose cyclic integral is 0. Let us think for a moment what kind of quantities can have this characteristic. We know that the cyclic integral work is not 0. Okay. It is good thing it is not. Otherwise, heat engine that work on a cycle such as steam power plants would produce 0 net work. Neither is the cyclic integral of heat. Now consider the volume occupied by a gas in a piston cylinder device undergoing a cycle as shown below. Okay. So, first it is expanded from 1 meter cube to 3 meter cube, then again compressed back. So, change in net volume is equal to 0 when the piston returns to its initial position. At the end of a cycle, the volume of the gas also returns to its value. Thus, the net change in volume during a cycle is 0. This is also expressed as change in volume is equal to integration over the path is 0. We see that the cyclic integral, cyclic is given by the oval sign on top of the integration, of a property is 0. A quantity whose cyclic integral is 0 depends on the state and not on the process path. Thus, it is a property. Therefore, the quantity delta Q net by T, and it is a reversible process, internal, must be a property. Consider the cycle shown below composed of two reversible processes A and B. Okay, A and B. Apply the Clausius inequality for this cycle. What do you conclude about these two integrals? 1 to 2, going from 1 to 2, delta Q by T, internal reversible process along path A, and from 1 to 2, delta Q net by T, internal reversible, okay, along path B. Apply Clausius inequality for the cycle made of two internally reversible process as, again, cyclic delta Q by net T internal reversible is equal to 0. Okay. So delta Q net by T internal review along path A is equal to 1 to 2 delta Q by net T internal review internal reversible process. They're both equal since the quantity delta Q net by T internal reversible is independent of the path and must be a property. We call this property the entropy, S. The entropy change occurring during a process is related to the heat transfer and the temperature of the system. The entropy is given by the symbol S, which is kilojoule per Kelvin, and the specific entropy is kilojoule per kilogram Kelvin. The entropy change during a reversible process, sometimes called an internally reversible process, is defined as ds is equal to delta Q net by T internal and reversible process. Or S2 minus S1 is integration from position 1 or state 1 to state 2, delta Q net by T internal and reversible process. Okay. So a cycle composed of reversible and irreversible process. In this case, delta Q net by T internal reversible is less equal to 0 because it is a mixture of reversible and irreversible process. So along path A is the first part, along path B is the second part. Okay. So the integral for the along the internally reversible process B, okay, is the entropy change S1 minus S2. Therefore, delta Q net by T plus S1 minus S2 is less equal to 0. In general, entropy change of a process is defined as change in entropy ds is greater or equal to delta Q net divided by T, where equal to holds for internally reversible process, greater than holds for irreversible process. Okay. Consider the effect of heat transfer on entropy for internally reversible case. In this case, ds is equal to delta Q net by T, which temperature T is this one. If delta Q net is greater than 0, then ds is greater than 0. If delta Q net equal to 0, ds is equal to 0. If delta Q net is less than 0, then ds is less than 0. Okay. The net subscript is to remind is that the Q is positive when added to a system, heat when added to a system is positive, and negative when leaving a system. Thus, entropy of the system will have the same change as the heat transfer in a reversible process. From the above, we see that for a reversible adiabatic process, no heat transfer, ds is equal to 0, s2 equal to s1. The reversible adiabatic process is called an isoentropic process. Entropy change is caused by heat transfer and irreversibilities. Heat transfer to a system increases the entropy. Heat transfer from the system decreases it. The effect of irreversibilities is always to increase the entropy. In fact, a process in which the heat transfer is out of the system may be so irreversible that the actual entropy change is positive. Friction is one source of irreversibilities in a system. The entropy change during the process is obtained by integrating the ds equation over the process. Okay, so delta S system is S2 minus S1 is greater equal to from position 1 to position 2 delta Q net over T kilojoule per Kelvin. Here the inequality reminds us entropy change in the system during an irreversible process is always greater than 1 to 2 delta Q by T, called the entropy transfer. That is, some entropy is generated or created during an irreversible process is that is some entropy irreversible process, and this generation is due entirely to the presence of irreversibilities. The entropy generated during a process is called entropy generation and is denoted by S-gen. We can remove the inequality by noting the following. Delta S is equal to S2 minus 1 is 1 to 2 delta Q net by T plus S generated. S generated is always positive quantity or 0. Its value depends upon the process, and this is not a property. S generated is 0 for an internally reversible process. The integral from 1 to 2 delta Q by T is performed by applying the first law to the process to obtain the heat transfer as a function of the temperature. The integration is not easy to perform in general. Now consider an isolated system composed of several subsystems exchanging energy among themselves. Since the isolated system has no energy transfer across its system boundaries, the heat transfer across the system boundary is 0. So delta S total is equal to from process 1 to process n, change in delta S is greater than 0. Okay. Applying the definition of entropy to isolated system, delta S is greater or equal to 1 to 2 dq net by T, which is 0 when it is adiabatic system. The total entropy change for the isolated system, delta S, is greater or equal to 0. Okay, the total entropy change of an isolated system during a process always increases, or in the limiting case of a reversible process remain constant. Now consider a general system exchanging mass as well as energy with its surrounding. Okay, so isolated system, there is a boundary, M is 0, Q is 0, work is 0. Okay, surroundings, okay, so M going in, Q and W, Q is going out, W is coming in. So we have S generated is equal to des delta S total is delta S system plus sum of all the delta S of the surrounding. where equal to holds, that should be greater equal to 0, where equal to holds for, so delta S total is equal to 0 for the totally reversible process, greater than 0 for holds for irreversible process. Thus, total entropy change, sometimes called the entropy change of the universe, or not net entropy change due to the process of this isolated system, is positive for actual processes or 0 for reversible process. The total entropy change for a process is the net amount of energy entropy generated during that process is generated, and it is equal to the sum of the entropy changes of the system and the surroundings. The entropy changes of the important system, closed system or control volume, and its surrounding do not have to be positive. The entropy for a given system, important or surroundings, okay, may decrease during a process, but the sum of the entropy changes of the system and its surrounding for an isolated system can never decrease. Entropy change is caused by heat transfer in irreversibilities. Heat transfer to a system increases the entropy, and heat transfer from a system decreases it. The effect of irreversibilities is always to increase entropy. The increase in entropy principle can be summarized as follows. S generated is equal to change in entropy delta S total is equal to 0 for reversible process, greater than 0 for irreversible process, and less than 0 for impossible processes. Okay. Entropy is a non-conserved property, and there is no such thing as the conservation of entropy principle. The entropy of the universe is continuously increasing. The performance of engineering systems is degraded by the presence of irreversibilities, and the entropy generation is a measure of the magnitudes of irreversibilities present during that process. Heat transfer is the area under the TS curve. For the reversible process, if the equation of ds, the equation for ds implies that ds is equal to delta q net by t. Hence, delta q net is t times ds, or the incremental heat transfer in a process is the product of the temperature and the differential of the entropy. The differential area under the process curve plotted on a TS diagram. Okay, so here we see an internally reversible process. The constant volume process has a steeper slope on the TS diagram than the constant pressure process. Area under the curve is the heat transfer. You're plotting T versus S. Okay. So Q net is integration from S1 to S2 T times ds. T. So temperature, integration of temperature with respect to S is the area under the process curve, is the heat transfer. In the above figure, the heat transfer is in an internally reversible process is shown as the area under the process curve, or area under the TS curve, plotted on a TS diagram. So Q net is integration from 1 to 2 TdS. For an isothermal reversible process, the temperature is constant and the integral find the energy change is readily performed. Okay. If the system has a constant temperature T0, the entropy change becomes delta S is equal to S2 minus 1 is from 1 to 2 delta Q net by T is equal to Q net by T. For a process occurring over a varying temperature, the entropy change must be found by integration over the process. Example, we have shown that the incremental heat transfer to an ideal gas in a closed system undergoing a constant volume process with constant specific heat is delta Q net is equal to du is equal to mCv dt. Therefore, for this process, change in entropy is T1 to T2 mCv dt over T, which is mCv ln T2 by T1. The change in entropy will depend upon the working fluid and the process. Adiabatic reversible isoentropic process. For an adiabatic process, one in which there is no heat transfer, the entropy change is delta S is equal to S2 minus S1 greater equal to 1 to 2 delta Q net by T. 0 adiabatic. So delta S is S2 minus S1 greater or equal to 0. If the process is adiabatic and reversible, the equality holds and the entropy transfer is delta S is equal to S2 minus S1 equal to 0. Okay, so S2 is equal to S1. Or on a per unit mass basis, S is equal to capital S by M and S2 is equal to S1 because the net change in entropy is 0. The principle of increase of entropy for a closed system exchanging heat with its surrounding at a constant temperature T surrounding is found by using the equation for entropy generated for an isolated system. A general closed system, a cup of coffee exchanging heat with its surrounding. Okay, so S generated is equal to delta S total is delta S system plus delta S surrounding summation greater or equal to 0. So delta S is equal to change in entropy of the system is S2 minus S1 of the system, or delta S surrounding summation is Q net surrounding divided by T surrounding. Okay, so Q net surrounding is negative, Q net surrounding is minus 0 minus Q out is Q out system. Effect of heat transfer on entropy. Let's apply the second law to the following situation. Consider the transfer of heat from a heat reservoir at temperature T to a heat reservoir at temperature T minus delta T greater than 0, where delta T greater than 0 as shown. Okay. Two heat reservoirs exchanging heat over a finite temperature difference. The second law for the isolated system composed of two heat reservoirs is S generated is equal to delta S total is equal to delta S HR at T plus delta S HR at T minus delta T. In general, the heat reservoirs are internally reversible. Delta S system is 1 to 2 dq net by T, delta Q net by T. So delta S HR at T is equal to minus Q by T. And delta S HR at T minus delta T is Q divided by T minus delta T. So delta S general is equal to delta S total is equal to minus Q over T plus Q divided by T minus delta T. Or delta S total or S gen equal to Q over T minus delta Q over T delta T divided by T minus delta T. Now as delta T approaches 0, delta S general approaches 0, S generated entropy generated equal to 0, and the process becomes totally reversible. Therefore, for reversible heat transfer, delta T must be small. As delta T gets large, okay, S gen increases and the process becomes irreversible. Find the total entropy change or entropy generation for a transfer of 1000 kilojoule of heat energy from a heat reservoir at 1000 Kelvin to a heat reservoir at 500 Kelvin. As shown in the diagram, the top heat reservoir is maintained at a higher temperature of 1000 Kelvin and the lower temperature, the lower heat reservoir is maintained at T minus delta T is equal to minus 500 Kelvin. So S generated is delta S total is minus Q over T plus Q divided by T minus delta T. So it is minus 1000 kilojoule divided by 1000 Kelvin plus 1000 divided kilojoule divided by 500. Or it is minus 1 because the first one 1000 cancel to leave minus 1, and the second term 500 divided by 1000 or 1000 divided by 500 is 2 minus 1 plus 2 2 minus 1 is 1 kilojoule per Kelvin. The third law of thermodynamics states that the entropy of a pure crystalline substance is absolute zero temperature is 0. This law provides an absolute reference point for the determination of entropy. The entropy determined relative to this point is called the absolute entropy. Entropy as a property, entropy is a property, it can be expressed in terms of more familiar properties, PVT through TDS relations. These relations came from the analysis of a reversible closed system and that does boundary work and has heat added. Writing the first law for the closed system in differential form on a per unit mass basis, we get delta Q net internal reversible is TDS, delta work internal reversible out is PdV. So TDS minus PdV is equal to change in internal energy. On a unit mass basis, we obtain the first TDS equation or Gibbs equation. TDS is du plus PdV. Recall that enthalpy is related to the internal energy by H equal to U plus PV. Using this relation in the above equation, we get TDS equal to DH minus VdP. These last two relations have many uses in thermodynamics and serve as a starting point in developing entropy change relations for the process. The successful use of TDS relations depends on the availability of property relation. Such relations do not exist in an easily used form for a general pure substance but are available for incomprehensible systems, liquids and solids, and ideal gases. So, for the general pure substance such as water and refrigerant, we must resort to property tables to find the values of entropy and entropy changes. Temperature entropy diagram for water is shown below. So you can see the dome. Under the dome you have saturated liquid vapor mixture. On the left of the dome, position 1, you have compressed liquid. On the left. On the right outside the dome you have superheated vapor in 3, position 3 or state 3. Okay. Shown here are the temperature entropy diagram, enthalpy entropy diagram for water. The HS diagram, called the Mollier diagram, is a useful aid in solving power plant problems where heat transfer and work may be expressed as enthalpy changes for steady flow, constant pressure, and isoentropic processes, respectively. Okay. Determine the entropy change of water contained in a closed system as it changes phase from saturated liquid to saturated vapor when the pressure is zero point 0.1 megapascal and constant. Why is the entropy change positive for this process? The water contained in a system piston cylinder device. Property relation, steam tables. Process and process diagram, constant pressure. Case the process relative to the saturation lines. Conservation principles using the definition of entropy change. The entropy change of the pure change of water per mass is given by this. The entropy change is positive. Heat is added to the water. Steam at 1 megapascal. This is example 7.6. 1 megapascal, 600 degrees Celsius expands to turbine to 0.01 megapascal. The process is isentropic and find the final temperature, the final enthalpy of the system, and the turbine work. Okay. System, the control volume is found by the turbine. Process and process diagram, isoentropic, sketch the process related to the saturation line on the TS diagram. Okay. Conservation principle, assume steady state, steady flow, one engine, one entrance, one exit, neglect kinetic energy and potential energy, conservation of mass coming in, rate of mass flow in is equal to rate of mass flow out is equal to rate of mass flow. First law of conservation of energy, the process is isoentropic and thus adiabatic and reversible. Therefore, Q is equal to 0. The conservation of energy becomes change in energy in is equal to change in energy out with respect to time, or M1 dot H1 is equal to M2 H2 plus workout. Okay. So workout is again, change in workout is M1 dot H1 minus M2 dot H2 or M is taken as a common is H1 minus H2. So W is equal to W dot out divided by m dot, which is H1 minus H2. Now let's go to the steam tables to find out the H, which are the enthalpy values. Okay. And at temperature 1 megapascal, temperature 600 degrees Celsius, H1 and S1 can be obtained. The process is isoentropic, so S2 is equal to S1 equal to 8.0311 kilojoule per kg. At P2 is equal to 0.01 megapascal, S is 0.6492 kilojoule per K, and S2 is equal to 8.1488 kilojoule. Thus, S1 less than S2 less than Sg. State 2 is the saturation region, and the quantity is needed to specify the state. Okay, so again, we have to work with the quality. Okay, X2 being the quality in position 2. Okay, plug it in. I mean, X2 is equal to S2 minus SF divided by SFG. And once we find X2, then we can calculate H2, which is HF plus X2 HG. Okay. And the work is H1 minus H2, which is 1153. The entropy change and isentropic relations for a process can be summarized as follows. Pure substances, any process, delta S is equal to S2 minus S1, kilojoule per kilogram Kelvin. Isoentropic process, S2 is equal to S1. Incompressible substances, liquids and solids, ds is equal to d a du divided by T plus P over T dV. The change in the internal energy and volume for an incompressible system is du is equal to C dt, and dV is 0. The entropy change for the new now becomes ds is equal to C dt by T plus 0. So delta S is integration from parts 1 to 2 C of T dt by T. So ideal gas, constant specific heats, approximate treatment, any process. Okay. So S2 minus S1 is Cp average my ln T2 minus divided by T1 minus R ln P2 by P1, and S2 minus S1 is Cv ln T2 minus by T1 plus R ln P2. Kilojoule per kilogram Kelvin is the unit, and you have X2 minus X3. Okay, so and that is equal to Cp ln T2 over T1 minus R ln P2 over P1. Okay. So P2 by P1 at constant entropy is equal to V1 by V2 raised to the power of K. Okay. And T2 by T1 at constant enthalpy, constant entropy is equal to P2 by P1 divided by raised to the power of K minus 1 over K. For an isoentropic process, this last result looks like P V to the power of K, exponent K, is constant, which is the polytropic process, and equation PVN is equal to constant with N equal to K. N is K is the ratio of the two specific heat pressure, specific heat at constant pressure divided by specific heat at constant volume. For TdS is equal to dH minus VdP, we obtain delta S is equal to integration from 1 to 2 Cp by Tpt dt minus R ln P2 over P1. Okay. And we are finding what is Cp over T dt from position 1 to 2. So we go from first T1 to T reference, then from T reference to T2. Okay. And if you change the order of integration, you get T reference to T2, Cpt dt by T dt minus, you change the order of temperature, T reference to T1. The integrals in the right-hand side of the above equation is called the standard state entropies, S sub 0 at state 1, T1, and state 2, T2. S0 is a function of temperature only. So S1 0 is from T reference to T1, CPT divided by T is equal times dt, and S2 0 is T reference to T2, CPT over dt is equal to CP function of T divided by T over dt. Okay. The standard state entropies are found in table A17 for air on a mass basis and tables A18 through A25 for other gases on a mole basis. When using this variable specific heat approach is to finding the entropy change for an ideal gas, remember to include the pressure term along the standard state entropy terms. The tables don't want you to do this. Isoentropic process delta S is 0, so S2 0 is equal to S1 0 plus R ln P2 over P1. If we are given T1, P1, and P2, we find S0 at T1 and S0 2P and then and S0 to calculate S020 and then determine from the tables T2, U2, H2. When air undergoes an isoentropic process, when variable specific heat data are required, there is another approach to finding the properties at the end of the isoentropic process. Consider the entropy change written as, okay, so bottom line is we get ratio of the extreme bottom ratio of pressures in an isoentropic process is related to the ratio of relative pressures. Okay, relative pressures means all the pressures are divided by the reference pressure. Okay. From TdS is equal to du plus PdV, we obtain for ideal gases delta S is 1 to 2 CVT by T dt plus R ln V2 by V1. When T1 is equal to T reference and V1 equal to V reference, T2 is equal to T, V2 equal to V1, and setting that entropy change equal to 0 yield. Thus, V by V reference S is equal to constant is exponent minus 1 over R integration from T reference to T CTT as a function of T divided by T dt. We define this relative volume as the above volume ratio. V F is the volume ratio necessary to have an isoentropic process between the difference temperature and the actual temperature. Is not used as a function of actual temperature. The parameter is a function of temperature only and is found in the air tables A17. The relative volume is not available for other gases in this text. Okay. So, for an ideal gas having constant specific heats and undergoing a polytropic process in a closed system, PV is equal to constant with N equal to K, the heat transfer by applying the first law. Based on the above discussion of isoentropic process, explain your answer. Compare your results, okay? So, aluminium at 100 degrees Celsius is packed in a large insulated tank having 10 kilogram of water at temperature of 30 degrees Celsius. If the mass of aluminium is 0.5 kg and the final equilibrium temperature of aluminium and water, the entropy change and the water and total entropy change of the universe because of the process. Before we work the problem, what do we think the answers ought to be? Are entropy changes going to be positive or negative? What about the entropy generated as a process takes place? So we need the process constant volume adiabatic no work energy exchange between the aluminum and the water. Conservation principle apply first law Q minus delta U. Q minus W is equal to delta U. So Q is 0. Work is 0. So delta U 0. Delta U system is delta U water plus delta U aluminum. Using the solid and incompressible liquid relation M water, C water, T2 minus T1 water plus M aluminum times C aluminum times T2 minus T1 for aluminum is equal to 0. Then we can find T1 plugging in the valve. From that we can calculate we know the change in entropy has to be greater or equal to 0. So we find the entropy change of the aluminum using this formula. Okay, I'm plugging in substituting in the values, and then we can calculate the delta S for water and then plug it in to get the S generated. Okay, so here there's another problem. Let me see how many more slides. Okay, we're almost done. So carbon dioxide initially at 50 kilopascal, 400 Kelvin, undergoes a process in a closed system until its pressure and temperature are 2 megapascal and 800 K respectively. Assuming ideal gas behavior and find the entropy change of the carbon dioxide by first assuming constant specific heats and then assuming variable specific heats. Compare your results with the real gas data obtained from the EES software. Assuming the table A2A data at 300 Kelvin are adequate, then Cp is equal to 0.846 kilojoule per kilogram Kelvin and R is equal to 0.1889 kilojoule per Kelvin degree Kelvin. Kilojoule per kilogram Kelvin. So S2 minus S1 is Cp average ln T2 by T1 minus R ln P2 by P1. If you plug in the values correctly, then S2 minus S1 is negative 0.1104 kilojoule per kilogram Kelvin. For the variable specific data, use the carbon dioxide data from table, and S2 minus S1 is ST2 zeros minus ST1 zero divided by mass of carbon dioxide is equal to minus R ln P2 by P1 and plus the answer is plus 0.0346 kilojoule per kilogram per Kelvin. Repeat the constant specific heat calculation and it is plus 0.0337 kilojoule per kilogram Kelvin. We observe that the 300K data give completely incorrect results here. Okay. And that's the end of it. I'll stop here today. If you have any question or comment, write me a note. Please give me a thumbs up if you really like this video. I would appreciate that. And if you like this video, please share with your friends. You and your friends, please subscribe to my channel by hitting the red subscribe button. And also, please do not forget to hit the notify button on the bell. So please click on the bell. You will be notified every time I upload a new video. And please do not forget to watch me tomorrow when I'll be back with another important problem too. I will discuss that. And please subscribe to my channel by hitting the red subscribe button. I have, solved all kinds of math problems, lectured on thermodynamics. So please come back tomorrow for my next video. Thanks for watching. Take care. Have a nice day.